In this video, we're going to combine the ideas from rates of reaction topic with Le Chatelier's principle, and we're going to go through some exam questions that relate to reaction conditions in industry and how they often a compromise between producing a high enough rate and a reasonable yield. In the chemical industry, we want to produce as much product as we can in the shortest amount of time. So we want a high yield of reaction and a high rate of reaction, but we also want to reduce the cost in producing these products in order for the company to be profitable. Often we have to raise the temperature to increase the rate of reaction. However, raising the temperature can reduce the yield of some reactions, as we saw earlier with Le Chatelier's principle. For reactions involving gases, increasing the pressure will increase the rate, as that will increase the frequency of collision of the reactant particles. However, as we saw earlier as well, increasing the pressure can reduce the yield of some reversible reactions involving gases. What we're going to do next is look at some past paper questions that includes this idea of producing a reasonable yield at a reasonable rate of reaction. So this is the past paper question, and we're going to look at question 4 of this paper. And this question says, in the chemical industry, methanol is synthesized by reacting together carbon monoxide and hydrogen in presence of copper, zinc oxide and alumina, which acts as a catalyst. This is a reversible reaction. High pressures and low temperatures would give a maximum yield of methanol. Explain why. So this question doesn't talk about rate of reaction, it only looks at yield. So we're not talking about the temperature affecting how fast the reaction is or how the pressure affects the rate of reaction. So we're simply looking at Le Chatelier's principle. So if we look at the equation here, the left-hand side has more moles of gas than the right-hand side. There's 3 moles of gas on the left-hand side compared to 1 on the right. So high pressure will favour the forward reaction to produce high yield of the methanol. The enthalpy change written here, which is usually written for the forward reaction, shows that the forward reaction is exothermic, so the reverse reaction is endothermic. So low temperatures will favour the forward exothermic reaction that releases heat to oppose that low temperature and raise the temperature again. So favouring the forward reaction also increases the yield of methanol. High pressure favours the forward reaction to produce fewer moles of gas on the right hand side of the equation. A low temperature will favour the forward reaction, which is exothermic, that releases heat to oppose the low temperature. The next part of the question asks us why the conditions we actually use in the chemical industry might be different to the ones above we mentioned earlier, where we say we want a high pressure and a low temperature to increase the yield of the product we want. However, there's problems associated with a high pressure in industry, and the main one is cost, because you need to generate the pressure using energy to do that. So also you need very thick wall containers. That has an added cost in the initial setup cost of the process. With some examples, they won't allow safety as an answer, but for OCR, they in the past have allowed the fact that running high pressures will have a safety issue associated with it because they could explode, I guess. With low temperature, well, the obvious reason is a low temperature will reduce the rate of reaction. So even though we've got a high yield, if we don't have a high rate of reaction, then it's not going to be useful to make the product in a reasonable time. High pressures will incur high setup costs for strong reaction vessels needed and high running costs for generating such pressures. Low temperatures will lead to a low rate of reaction and will be too slow. So you've got another OCR paper for 2012, and we're going to look at question 3. Hydrogen has many industrial uses, including making margarine and ammonia. Well, making margarine is the hydrogenating of vegetable fats, that's unsaturated fats, that's hydrogenating alkenes, and making ammonia is the Haber process. Hydrogen can be made by the reaction between methane and steam. Well, this is the reaction I talked about earlier, which makes synthesis gas, which is a mixture of hydrogen and carbon monoxide, and the forward reaction is shown to be endothermic. The pressure of the equilibrium mixture is increased. Explain what happens to position equilibrium. Well, increases the pressure will favour the side of the reaction with fewer moles of gas, which is the left-hand side, where there's 2 moles of gas compared to the 4 on the right. So the equilibrium will shift to the left-hand side. So increasing the pressure favours the reverse reaction to produce fewer moles of gas and oppose the increase. So position equilibrium will shift to the left-hand side. The temperature of the equilibrium mixture is increased. Explain what happens to position equilibrium. Increasing the temperature will favour the forward endothermic reaction to oppose the change, so the position equilibrium will shift to the right-hand side. The reaction is actually carried out in the presence of a nickel catalyst at a pressure of 30 atmospheres, suggests why the manufacturer uses 30 atmospheres. So we look at the early part of the question. Increasing the pressure actually shifts the equilibrium to the left-hand side, so therefore the yield of the hydrogen is going to be decreased. So why do we want high pressure? Because 30 atmospheres is 30 times the atmospheric pressure. So there must be a reason for that, and the reason is the rate of reaction. A higher pressure will increase the rate of reaction for gaseous reactants, but not high enough to produce a yield. We'll do one more, which is 2015, and question 3. So question 3 talks about another way of making methanol, which is using carbon dioxide and hydrogen, and the forward reaction is endothermic, and they're all gases. The left-hand side are 4 moles of gas, and the right-hand side is fewer, and it's 2 moles of gas. We're going to skip these questions and go straight to part C. Part C says the high pressures and low temperatures will give a maximum yield of methanol. Explain this statement in terms of the Chatalis principle. So we go back to look at the equation. A high pressure will favour the forward reaction to produce fewer moles of gas, and also the low temperature will favour the forward reaction as well, which is exothermic. So the forward reaction will produce heat to increase the lower temperature. High pressures will favour the right-hand side with fewer moles of gas to oppose the high pressure. Low temperature will favour the forward reaction, which is exothermic, to oppose the low temperature. And both these conditions will shift the position equilibrium to the right-hand side for a high yield of methanol. And finally, explain why the actual conditions used by the chemical industry might be different. Well, first of all, high pressures are too expensive to generate. And secondly, low temperatures would lead to a low rate of reaction. So the actual chosen conditions will be a compromise for producing a reasonable rate of reaction and a relatively good yield.